Hi, welcome to API 304, building next-gen applications with event-driven architectures. My name is Sam Dingler. I'm a Principal Solutions Architect with AWS, and I'm joined today by Robbie Kohler, Director of Software Engineering with Taco Bell. Our agenda today has three main focus areas. The first is a deep dive into enterprise integration patterns, followed by a review of some principles of event-driven architectures, and then I'll be turning it over to Robbie to tell us more about Taco Bell's order middleware service and their applications of these patterns and best practices in real life. So first, let's talk about some enterprise integration patterns. You'll notice as we talk through these patterns, I'll be using the word coupling quite a bit. And coupling is a really important concept to understand when we're thinking about our architectures and the trade-off between tight and loose coupling and the decisions that we make. Coupling is a measure of the dependencies between different systems that are in coordination. The coupling has a cost, both at runtime and at design time, and it's not a single choice that you'll make for your full architecture. You'll make decisions on what type of coupling to adopt in many different aspects of that architecture. It's also important to notice that it isn't a one-dimensional choice and that we can think about coupling through many different facets. We're thinking about the different ways to conceptualizing and applying coupling in our architecture. This could be in the facet of our dependencies around technology. So what technology are we choosing to implement part of our systems, and how can that be different than other parts of technologies and other systems? It could be around location dependency. So how aware are our systems directly of the address of something to communicate with versus looking those things up in a registry and having a layer of independence and lookup, and so flexibility in determining the location of those services. A very popular one in talking about coupling is temporal coupling. Temporal coupling means that whether our systems need to communicate in near real time, where they expect request and response to happen at the same time, or if we can have asynchronous communication where those things can happen at different times. Regardless of the type of coupling you adopt, this quote from Gregor Hoppe is important to consider in your design choices. The appropriate level of coupling depends on the level of control you have over the endpoints. In cases when you have more control, you might choose tighter coupling where it makes sense. And there are cases when you have less control where loose coupling makes a better fit. And Robbie will be discussing this concept in their design choices as they evolve the architecture of Taco Bell. Let's talk about our first pattern, the synchronous request response model. So in this model, we have a sender and a receiver, and the sender sends messages as a request to the receiver. The receiver processes those requests and sends a response back as a response. Now there's certain advantages of synchronous request response model. The first is there's no additional latency in the communication. So there's no baggage as we're trying to communicate between these two parties. The second is that it's simple to describe and to understand and to troubleshoot this type of communication pattern. Last is, if there's a problem with the receiver, the sender can fail fast. It can understand that there's an issue and can decide what to do next. However, there's some disadvantages as well. The first is that in order for this type of pattern to work, both the sender and the receiver have to be working at all times. If the receiver has a failure, then the sender has no option on how it can communicate, and it is directly impacted by any failures of the receiver. Another case is when we have a large number of senders that send a large number of requests, more so than a receiver might be able to process. In this case, we say the receiver is being throttled and it can't handle the number of requests. And so this can cause issues based on bursts of traffic where receivers might not be able to handle that sudden traffic burst. And so here, it's especially a problem in large systems because as receivers come back online, then they get a flood of traffic from senders that have been waiting to send requests to the receiver, and that can immediately knock down the receiver. We call this the thundering herd problem, and it can be especially challenging for distributed systems like this at high scale to recover. So to address these disadvantages, we can adopt an asynchronous point-to-point model using a queue. In this case, we still have a sender and receiver, but we've introduced an intermediary, a queue, in order to buffer the communication between the two. In this case, senders send messages to the queue, which are acknowledged by the queue, and receivers can separately come and pull messages from the queue and acknowledge the successful processing of those messages. The advantages here is we've decreased the amount of temporal coupling. No longer do the request and response have to happen at the same time. They can happen at different times, which is where the asynchronous communication aspects of this architecture come into play. The second is that this system is more resilient to failures of the receiver. If the receiver fails, the sender can continue to send messages to the queue without being directly impacted. And because the queue is a buffering mechanism, in the case that we get a large number of senders or a large number of requests from senders, the queue helps us buffer that traffic so that the receiver can choose the rated consumption of the messages that it might prefer, regardless of the amount of traffic that's incoming. So it helps us create more resilient architectures that can survive unexpected behaviors in the overall system. Oftentimes in a queuing solution, you'll see something mentioned called a dead letter queue or a DLQ. The DLQ is a mechanism by which the queue can have an alternative place to send messages when a receiver is unable to process those messages after a certain number of retries or after a certain period of time. You'll see DLQs mentioned across many AWS services, and whenever you see one, it's a best practice in order to configure it so that we don't accidentally lose messages as they move across many AWS services. So if you see a DLQ, best practice is configure it, monitor it, and have a process around analyzing and responding to messages on the DLQ. Another aspect of how we can scale the receivers in an asynchronous point-to-point solution is that we can increase the number of receivers in a horizontal way. And here we have a pattern called a competing consumer pattern. And what that means is even though we're increasing the number of receivers and therefore can increase our capacity to process messages off a queue, in a queuing solution, only one receiver can consume a message at each time. And here the receivers can each have an opportunity to process the message. If it's unable to process it, it can go back to the queue and another receiver can try to process it. But again, after a certain period of time or a certain number of retries, that message can go DLQ for error handling. Now there are a couple of disadvantages or considerations when adopting a queue. The first is response correlation. So when we have synchronous communication, it's very easy to coordinate which response is coordinated to whatever request was sent to it because we have synchronous communication. In the case we have asynchronous communication, we need to identify a correlation ID that we can put on the message that the receiver can include in the response. And that response can go over a different channel. Maybe it's another queue that the response sends the message to with the original correlation ID so that the sender can monitor that and identify which responses are associated to the original requests. The second case is when there's failure. Now, it's great that we have this asymmetric traffic and this buffering mechanism in the case of receiver failure. However, when receivers come back online, there's a decision to make. So not only are we now trying to process new messages that are coming to the queue, we've developed a backlog of messages that were accumulated while the receivers were offline. The receivers now have a decision to make. How do we balance processing the backlog with the new messages that are coming through? There's a couple of different strategies, but one popular one is that we have another queue that we've set up, and as the receivers pull backlogged messages off a queue, they can re-queue it on a backlog queue to process those out of band so that new messages are processed very quickly. Another option is that in the case when we have a shared queue, right, where we have many senders that are sending messages, and we have a case where maybe one sender is sending more messages for a particular tenant where we have a shared queue. This can cause issues where we don't have fairness across the processing of messages for all tenants on a queue. So here we have a couple of options in how we address that. First is we can introduce throttling on sending messages to a queue so we get even distribution and back pressure on publishing messages to the queue. The second is if you have a particularly high volume tenant in your system, then you can create a dedicated queue for that tenant and sideline the messages to that queue so that you get fairer processing of messages on a shared queue across the other tenants. Now, when we're thinking about an AWS service to use to fulfill the point-to-point asynchronous model, SQS, the Amazon Simple Queue Service, is a great option for that. SQS is a fully managed distributed messaging queue. It scales almost infinitely on both the senders and receivers. You're only limited by how many of those that you can run on both ends. You're able to publish messages singularly or up to batches of 10 messages. And so it's a great option as you're looking to scale both ends of your architecture, and it's a very popular mechanism for buffering communication between systems. It's really easy to use. It's a simple API that allows you to create queues, manage queues, and also send and receive queues as well. It also supports the dead letter queue option that we mentioned, and it comes in two varieties, a standard and a first in, first out, or FIFO option. Another option is Amazon MQ. Amazon MQ is an open source, managed open source software. It comes in two different varieties, ActiveMQ and RabbitMQ. And in this case, you get to use the same open source software that you're familiar with, and with with AWS actually managing all the operational responsibility of provisioning and making sure that the message brokers are highly available, all our best practices from operational point of view are yours to use so you can stay focused on how you use those queues. This means that it's less code for you to change inside of your clients. You can use the same open source clients and protocols that your applications might already be using. So this is a very popular option when you're operating in a hybrid scenario or when you're doing a migration into AWS before you do a refactoring. Okay, let's look at another model. This is the asynchronous point-to-point model using a router. In this case, we have senders and receivers, but we need to decide where those messages need to go, which receivers need to receive which messages. And here we have blue messages and green messages, and we have a blue channel and a green channel, and receivers tied to both. In this case, the sender has the logic on how to send those messages to the blue channel or the green channel. This has some disadvantages over time. We've increased the location coupling between the senders and the receivers because the sender needs to know what the blue and green channels are and have the routing logic on how to send those messages to those. So when we have a simple case of 2 channels and very simple logic, this isn't so bad. But as we increase the number of receivers or increase the complexity of the logic, this becomes a problem in our architecture. And is a really good example of tight coupling. Tight coupling means, of course, that as our architectures change over time, if we find that there's friction or there's difficulty in changing our systems, then that is a sign that your system is too tightly coupled. So in this case, every time we need to add the receiver or change the business logic, we would, add receivers or change the business logic, we would have to go into the sender and change the logic and touch it every time we wanted to make a change. So it's a really good example of where we have too tight coupling between senders and receivers, and we need to introduce an intermediary to address it. So in this case, we can have the same model, but instead of doing point-to-point routing of those messages, we can do that using an event bus instead. So in this model, we still have senders and receivers. We have blue messages and green messages, but instead of the sender having the requirement to have the routing logic, we can have an intermediary called an event bus where we can position that routing logic instead. So here, the responsibility of the sender changes a little bit. The sender has to collect the context for a message, whether it's a blue message or a green message, and attach that context to the message that's published to the event bus. But after that point, the responsibility of the publisher is done. It doesn't need to change the behaviors of how it applies context and calculates context depending on how many receivers come or what those rules are. It just needs to capture the context that can be used for routing purposes. On the other hand, we have receivers that can come and write their own rules and filters on which messages they're interested in processing. And it can do that independently without impacting the sender. So here we've decreased the coupling from the senders and receivers, and our architecture is more flexible over time. It's also more efficient for both the sender and the receivers to be able to publish the context of the message once and have receivers only process the messages that they're interested in. So there's less waste in processing messages that don't apply. When you're using AWS, there's a service for this. It's called Amazon EventBridge. Amazon EventBridge is a fully managed serverless event bus, and it's focused in 4 main areas. First is the source of the events. EventBridge allows you to ingest events from AWS services, things that are already happening in your AWS account. You can have your own custom events from your own custom applications, and you can ingest events from some of our SaaS providers as well. Regardless of that event source, those events will land on an event bus. We offer default event buses for AWS service and scheduled events. You can have one or many custom event buses for your applications, and events from our SaaS partners go to a partner event source. Regardless of where those events land on which event bus, subscribers can come and write rules against those events and then directly target AWS services to handle and process that event. So EventBridge is very well suited when you have a lot of complex routing requirements and you have rules that you need to be able to describe exactly in a fine-grained way what messages are important to the subscriber and then directly target AWS services without other intermediaries or proxies. This is what an example event looks like in EventBridge. It has a JSON structure. Events are really split in two main areas in the fields that they have. The first is the envelope fields. So here you can have, you see we have a source and a detail type field. And together, the source and detail type help us identify the shape of the event, or sometimes called the schema of the event. The actual data of the event is contained in the detail field. And by convention, we recommend customers include a metadata and a data field. The metadata field contents include your own custom envelope fields that you might like to include for your event. And the data field can include whatever custom data that you would like to include. So again, these are not hard requirements. You can put any data that you would like in the detail field, but this is a convention that we found is very successful for customers. Now, in order to write a rule, you can also express that as a JSON structure as well. EventBridge can process with their rules the full payload of the event. So you can use fields and subfields in the description of your rule. And when you've identified the field that you want to match on, then you can provide an array expression on the types of values that you're looking for. In this case, we have a list of strings. So this is an allowed list where we're looking for exact string match, where the currency should either be AU or NZ. In our sample event, we see that our currency is AU under the detail data currency field, so we would consider this a match. So this is a simple example of doing an exact string match on a list of values, but we also support deny lists on exact strings. We can do string prefix matching. You can do numeric exact matching, numeric range matching. You can see if fields exist or not, and if they have null values or not. And you can include multiple fields in your rule as well. So it's very easy and to have very expressive descriptions of the types of data that you want to process. Now, if an event matches a rule, this is where we can directly target an AWS service. Today, EventBridge supports over 20 AWS services that you can send to directly, and it supports API destinations. API destinations is an outbound webhook mechanism where EventBridge can send HTTP requests to public endpoints. It's very flexible on the structure of the events and the requests that you create. It also supports 3 different auth mechanisms. It supports basic auth, API key auth, and OAuth credential flows. There's another interesting feature with EventBridge too, especially when you're dealing with your partners and who you want to send webhooks to, and that is a throttling mechanism inside of API destination. So let's say in your system, you can produce lots of events, but you're partnering with another system where you want to send HTTP requests that maybe can't scale as high as your system can. In the same way that we were talking about our senders and receivers earlier in the synchronous and asynchronous point-to-point examples. So in this case, you can specify a maximum TPS or throughput limit, and EventBridge will respect that and not send any more number of requests than specified that, and will handle the retry and exponential backoff of sending those events for you. So it's a really handy feature when you're worried about potentially overwhelming your outbound partners. Okay, let's dive into some aspects of event-driven architectures now that we've talked about the patterns and enterprise integration. So if we're going to talk about event-driven architectures, let's talk about the properties of an event first. So events are simply signals that a system state has changed. Outside of all this architectural and technology conversation, you'll recognize that events are happening around us all of the time. And we can observe events that are happening and choose to react to them or not. It's important that we recognize that events occur in the past, and often we will name our events with a convention to reinforce this. So we will use a noun, which is the state, and a verb in the past tense, which is the change of that state. So here we have an example called order created. This is a convention, it's not required, but again, it helps reinforce this concept that events occur in the past. Because events occur in the past, that means we can't change them. We call this that events are immutable. Now, if we want to change the effect of an event, we can always emit another event and react to it and reverse the outcome of the processing, but we can't go back in the past and change the properties of an event that occurred. Now, we'll talk next about information to include in an event, but you can consider the data that you choose to put in an event as another form of coupling between your producers and consumers. The more information that you put in an event, the more coupling that you create in a semantic way between your producers and consumers. Now, when you're considering a strategy on data to put in events, you really have 2 extremes. You can either have sparse events or you can have full state descriptions. Sparse events only include the details of the state that was changed. These might be IDs of systems and values that were changed. Full state descriptions include that, but more information, more business context. In this case, we're including the order status and the order value as well. Now, these are two ends of the extreme, and often we pick in between. And to help guide that, there's a couple of things that you can think through. The first is, in the case of sparse events, if you don't have enough context in the event and you have a large number of subscribers, then those subscribers are all going to want to come back to the source of truth to get more context based on that ID. So in the case of large number of subscribers without enough information in the event, you can create a reverse flood of traffic or a reverse DDoS to your source of truth. Now, in the case when we have too much information, where we've included all of the context in the event, this can be an issue as well. And that's because we want to prioritize that our event schema should be backwards compatible in the same way that we would think about our API structures and contracts as well. So we want to be judicious and intentional about the data that we put in events because it can be difficult to remove it later on once our consumers start expecting that certain schemas or values exist. One challenge is that there is a cost to calculating those values that we put in an event. Maybe when we start with an event structure, that cost is small. Maybe all the values come from a single database table or a single microservice. But if we refactor our systems over time and decompose monoliths or microservices into multiple systems and separate that data into multiple databases or tables or systems, then the cost of calculating and joining all that information back into an event can increase over time. And we don't want to remove data over time because we want to maintain that backwards compatibility. So my recommendation is start with sparser events, learn about what are the common properties that are applicable across most of your subscribers, and include that in a very judicious way, and just add that very intentionally and analyze when you need to add them and take that step very carefully and thinking about the cost of that over time. Now, when we communicate events across a bounded context or business domains, we call this choreography. And this produces very loose coupling between the communication between different domains. In this case, we have a retail and fulfillment domain. A very important concept in choreography is that the publishers of events cannot have an expectation for how that event or if that event will be processed by a subscriber. The responsibility of the publisher is to pull the context in the event, adhere to backwards compatible schemas, and to successfully publish that event to an intermediary like an event bus. And that is the end of the responsibility of the publisher. When the publisher has more expectations on what will happen after that point, you're starting to introduce tighter coupling in the behaviors of your system. So when we have two business domains that want to participate in choreography, we do that through a pub-sub model. In this case, a business domain that's interested in events that are published will subscribe to a publisher domain where that event can be found. And whenever an event occurs in the publisher domain, an event will be published to the intermediary like an event bus. Again, the publisher has no awareness if or how that event is received and processed. But in this case, the fulfillment system can receive the order created event and process it in its own business context. It may choose to remove that subscription, or another system may come to add the subscription, but the behavior of the retail domain doesn't change. Now, because we are communicating in a distributed way across business domain and microservices, we are very quickly in the world of distributed systems and subject to things like the CAP theorem. In that, we have to choose between correctness and availability, and oftentimes we'll find that events are communicated more than once so that we can trade off on the fact that events are not lost. So this is called event duplication. And when we have receivers that need to handle this problem, these receivers need to be built with idempotency in mind. Idempotency means that receivers can receive the same event twice, but it can have the same outcome without side effects for duplicate processing. Now, it's important when we want to help our receivers achieve idempotency that the sender puts a token called an idempotency key into the event that the sender calculates and puts in the event so that clients and receivers can easily determine if this is something they've seen or not. It's very important that the client does this because in the case when the client doesn't have an acknowledgement that the event was received, it might need to recalculate the idempotency key, and you want to do that in a deterministic way. So the client puts an idempotency key on the event, sends it to an intermediary like a bus, and then receivers receive those events and have to achieve idempotency. Well, how do they do that? So there are various event deduplication strategies, but one popular one involves storing that idempotency state in an external database. And another important aspect of this is when you store this idempotency key in external database is that you determine the length of time in which that idempotency is evaluated. So if you were to look at our SQS FIFO and SNS FIFO solutions, you'll see that this period is 5 minutes for those services. 5 minutes might be a good fit for your systems, or you might choose less or more time based on your use cases. Now, we have the idempotency key, we have a concept around time and a place to store it. How does this actually work? Well, here we have a diagram from the Lambda Power Tools Python idempotency library, which there's a link for below that I encourage you to check out, both as a reference architecture and as a Python library you can include in your projects to make this process simple for you. So in this case, the client sends an event to something that can process that event. And here, in this case, it's a Lambda function, and that event includes the idempotency key. The Lambda function checks an external data store to see if that key exists. If it doesn't, it records the fact that it's processing that key, handles the event, and then stores the result in the persistence store. In the case that that result can't be returned to the client is naturally going to retry the request in order to get a result using the same idempotency key, right, the second time. That's a really important aspect of this solution. In this case, when the client sends an event with the same idempotency key, the Lambda function checks the external data store, sees that it's been processed before, has a result, and simply returns that result without reprocessing and handling that event. So this is how you can achieve idempotency, and this library can make it easy for you to do so. There's another resource that you can look at. It's an article called Making Retries Safe with Idempotent APIs. This comes from our AWS Builders Library, which is our collection of best practices from our senior principal engineers over many years of building and operating AWS services, and I encourage you to check it out. Okay, now there are going to be cases when we do need more deterministic and tightly coupled communication outside of choreography. And often these requirements come into play inside of a business domain. So let's say an API request or an event occurs and hits a microservice. Well, that microservice or API might have requirements around the sequences of things that need to happen, how to handle errors and retries in order to implement a business process in a deterministic way. So in this case, we have a retail domain that receives an order request, communicates with an inventory manager. The inventory manager has to check the stock and then communicate with an invoice manager. The invoice manager then creates the order, and an order created event is produced by the retail system as an event that can be consumed out by another business context. But that process in between is a workflow. It's a tightly coupled business process by design. In order to process that, we call that orchestration. And the thing that handles the execution of that plan is called the orchestrator. Now, in the past, orchestrators came with a high cost. They were usually single points of failure, they were large systems, difficult to scale, and had high licensing costs. AWS has a service to help you do this called AWS Step Functions. Step Functions is another serverless, fully managed service that allows you to describe workflows as state machines. State machines have a series of tasks or flow controls that you describe, and then as the execution of that state machine happens, we transition between those things in a deterministic way. You can be very specific about the sequences of actions and how you want to handle errors and retries in a way that's tightly coupled toward the business process that you're trying to achieve. The tasks and flows that you create within a step function workflow are easy to change and reuse in the same workflow or even across workflows over time. So it's very good for composability. Here you have a screenshot of the Step Functions Workflow Studio. This is a new feature in Step Functions where you can design the workflows using a visual editor and produce something called the Amazon States language, which is a special domain-specific language that was created for Step Functions and is open sourced. So when you are creating workflows, whether you do it through the visual editor, whether you edit the DSL yourself using YAML or JSON, whether you use the Cloud Development Kit in your favorite programming language, or our data science SDK as a Python library that you can use in Jupyter Notebooks, all of these forms of authoring produce a DSL, the domain-specific language, which represents a declarative view of your workflow. That workflow can be visualized. This is really helpful when you're trying to validate the correctness of the workflow and communicate business processes across various stakeholders in your organization. The other aspect of step functions beyond the authoring and visualization, which is important, is the execution of those workflows. Step functions has horizontal execution, both of the decision logic at each step in the workflow and its integrations. And every step that happens inside of an execution of a workflow is audited for you automatically and stored inside of either a database for the standard workflows or logging both for our standard and express workflows. But essentially you get a tight audit log of timestamps and integrations and everything that happens across every integration just as part of this using the service. There's two types of integrations that we support in step functions. The first is our optimized integrations, and the second is the AWS SDK integrations. Optimized integrations support over 17 different AWS services and has an optimized developer experience and how you include that integration in your workflow. It supports 3 different integration patterns: the request response, wait for a callback, and run a job. The AWS SDK integrations is new, and this allows you to integrate directly with over 200 AWS services and over 9,000 different AWS SDK calls directly. This supports the request response and wait for a callback integration pattern. Let's take a look at how those work. So in the request response model, here we have a workflow where we're going to get an object from an S3 bucket. We'll call a Lambda function to do a transformation of the data in that object. And then we will take that context and publish it as an event so that other bounded contexts can subscribe and process the result of this business process. So to do so, we would use a request response to S3, and it's a synchronous request to get the result back. We can make a synchronous request to a Lambda function to do the transformation and get the result. And then we could choose an asynchronous request to the EventBridge service to publish the event, get an acknowledgement, and complete the workflow. So we support this request response across these optimized integrations, and it's also supported across all AWS SDK integrations. Whether the interaction is synchronous or asynchronous, it just depends on what that AWS service and their SDK supports for that particular API call. The next is a wait for a callback mechanism. Robbie is going to dive deeper into how Taco Bell uses this pattern in their architecture. In this case, we have an asynchronous mechanism for workers to perform work and report back success or failure. So here we're using a queuing mechanism in order to queue work that a fleet of workers could pull and execute work for. Here what can happen is we can introduce something called a task token in our message that we send to SQS along with the other messages context that's needed for processing it. Our fleet of receivers can pull messages off the queue as we described from earlier, process the message, and in the case that there's a problem processing the message, it can use that task token to send back to step functions that there was an error. That error can have a reason and a description behind it, and then the step functions workflow can catch that error inside of the workflow description and decide how that should be processed. If the message can be processed successfully, then instead the receiver can send task success with the task token and optionally data, and that can follow a different flow inside of your workflow. Now we support the optimized integrations across these services, and the callback task token is supported across all AWS SDK integrations. The last integration pattern we have is the run a job. And in this case, step functions is operating a fleet of pollers or event-driven mechanisms to help you monitor asynchronous jobs. So here we have a case where we're going to use Athena. Athena is an on-demand query service where you can query data that's cataloged through the Glue data catalog, and it's an asynchronous process. So here we can have a request where we're kicking off a query job with Athena. Now here, step functions will monitor the process of that, and when it's complete, then it will continue the workflow with the result of that process. Followed by that, we might want to collect the results. So here we could use a request response with a sync request in order to get the data results and send that back. And again, we could conclude with an event where we're doing an asynchronous request to EventBridge, getting acknowledgement, and that can complete our process. So this is handy when you're looking for a managed way in order to integrate with these optimized AWS integrations. We do not support the AWS SDK integrations with this pattern. So we talked about two forms of integration. We have the very loosely coupled choreography and the tightly coupled orchestration. But in my conversations with customers, these are often used together. So we will have APIs or events that will drive tightly coupled business processes, which may just be 1 or 2 steps in what you might typically think of being accomplished in code as a response to an API request, for example. And then after that business process is complete, it can emit an event That event can hit an event bus so that subscribers can come and receive that event and process that event in their own business context, which may include its own workflows and forms of orchestration. So events to workflows to events is becoming a very common pattern and very easy to implement in AWS now that we have serverless services to help you focus on the solution and not the operational responsibilities of the architecture and infrastructure. So next, I'd like to turn it over to Robbie, the Director of Software Engineering at Taco Bell, and he's going to tell us more about the order middleware service and how Taco Bell took these concepts and best practices and put them in place in a real-life architecture and to have tremendous results in applying a serverless architecture with event-driven patterns. Over to you, Robbie.
Thanks, Sam. Hey, everyone. My name is Robbie Kohler, and I am Director of Software Engineering at Taco Bell. I'm so excited to be here today to talk about Taco Bell and the ways that we are using AWS and serverless to improve our business, operations, and the customer experience. Let's start with who we are. Taco Bell is the largest Mexican-inspired food brand in the United States with over 7,000 restaurants. What's exciting is we're also expanding rapidly internationally with 600 restaurants and plans to open to 2,000 by the end of the decade. We're also heavily involved in the community. We've given away over $110 million through our Taco Bell Foundation to young people. And with that many restaurants, we deal with a lot of scale. We serve over 42 million customers per week, and that comes out to 1 billion unique orders per year. If you've never had Taco Bell and you're planning to be in Vegas for the reInvent conference, I highly recommend you check out the Taco Bell Cantina. It's right there on the Strip. It's one of our flagship locations. It's 2 stories. It has fun specialty drinks, and it's just a really fun place to be. Let's take a look at the different ways a customer can order through the digital channels. We have our e-commerce mobile apps, which is our native iOS and Android apps. We have our e-commerce web app, which allows a customer to use their browser or mobile browser to order our food. We have kiosks in roughly 7,000 restaurants, which allows a customer to use a digital display when they're on site. And we have integration with major delivery partners, which we're going to talk about a lot more today. We have a plan to grow to 50% of all orders through digital. With this, there's going to be plenty of challenges with scale, so we plan to do this serverless first. Let's take a look at our journey at Taco Bell with AWS. In early 2018, we wrote our first Lambdas. We were comfortable with C# and Java at the time, so we dipped our toes that way. We saw the potential. A few months later, we released the menu middleware platform. This was a major system that allowed us to integrate our menu data in real time to partners like our delivery partners. We actually chose to use serverless components for the system in several places. It was the first time using serverless in such a mission-critical system, and it was a huge success. We continued to build more on serverless, and we reached another milestone in 2019 when we were in 7,000 restaurants with our kiosks, powered by a completely serverless backend. Early 2020, we were becoming more serverless first. We built the Diablo platform. Diablo stands for Data Integration and Automation Batch Lambda Orchestration. It's also the name of our hottest sauce. We built basically a service on top of step functions and Lambda functions that completely streamlined all of our data integration and ETL jobs. It was a huge success. Later in the year, the world changed and we released the Order Middleware platform. We're going to talk about that next. That brings us to today, where we are a fully serverless first dev shop. We have over 30 plus serverless apps and growing. Let's take a closer look at one of those fully serverless applications called the Order Middleware. In the middle of 2020, the world changed overnight and consumer habits changed with them. All of a sudden, there was an immediate spike in demand for delivery. We knew we had to act fast to serve our customers. We worked with our delivery partners, and they provided tablets to each restaurant to integrate. The way that it would work is that our customers would place their orders on their favorite delivery partner app, and those orders would be forwarded to the store to the tablet. The Taco Bell employee would see the order and have to double enter it into the point of sale. As you can imagine, there's a few disadvantages with this approach. One, it's distracting. The team members are always very busy There could be long lines in the drive-thru, and just having to watch these multiple tablets was just very distracting to them. Secondly, it's inherently error-prone. Some of our orders are really large and complex with modifications, so it's only natural it would be hard to get them always right. We knew this was not the long-term solution. The better solution was to integrate directly with the point of sale from the delivery partners. Here you can see that the orders would come again from the customers on the app, but instead of going to the tablet, they would be sent via a webhook to the cloud, to our POS API, and we would inject those directly into the point of sale. Much happier Taco Bell employees because they would no longer have to look at the tablets. So you might be thinking, well, this seems pretty simple. Why would you need a system that handled this? Well, we identified a few challenges early on with this. One, again, we deal with a lot of scale, and we're planning to do 50% of all orders through these systems. So we wanted something that would scale elastically and we wouldn't have to worry about. Two, we wanted a system that can handle retries and things like timeouts very easily with minimal toil. As Werner says, everything fails all the time. And if you've ever moved anything to production, you know how true that is. And then there were rules that made it seem a little bit more complex. We had to handle stores being offline, hours being matching up, the products actually being available, and ability to cancel the orders at various parts of the workflow. It definitely became more complex as we looked at it. And finally, we wanted to build a very flexible and adaptive system. We knew we were going to add more integrations to this. This was not going to be a one-off project. So with that in mind, we went out to try to design the system. At the time, EventBridge was a relatively new service in AWS. We liked that it was serverless, and we knew we were going to build a 100% serverless solution. Because it dealt with events, and we were getting these explicit events from our delivery partners, we thought it would be the perfect choice to start with. So we started with a choreography approach to design this. Let's walk through an order-placed event. Here the customer places an order through their app, and the delivery partner forwards an event to us. The order-placed event will go to our API gateway. We'll directly forward that to EventBridge via service integration with no Lambda required. And EventBridge will then fire off rules. In this case, we have a rule, basically listen to a specific source and specific detail of the event for order placed. This might call an adapt order function. That might do some validation and convert the order to maybe a canonical format. If that succeeded, the order would be sent back to EventBridge with an adapted event. At that point, the second step would happen. The adapted event would then fire another rule, accept order. So if you ever use one of these apps and you saw that your food was accepted by the restaurant, this is essentially what would happen. We'd communicate with the delivery partner API, accept it, and then send an accepted event back to EventBridge. At this point, EventBridge will fire another rule which may create the order on the POS. Creating the order is actually connecting to our POS API and injecting the order into the POS or point of sale device in the store. Then we'd send a created event back to EventBridge and so on. Other events from the delivery partner would be handled similarly and choreographed with EventBridge. At this point, we realized this would work, but we decided to ask ourselves a few questions if this was the right design. First, we asked, is this hard to reason about? Is this hard to understand? Well, we found very quickly, if you didn't architect it or build the Lambda functions and the rules, it was actually kind of hard to explain it to someone else, like a product owner or a quality engineer. We'd sometimes even get lost going through this diagram and going through the different arrows. So we would say it was hard to reason about. Second, is this too loosely coupled? We all know loosely coupling is usually a good thing, but there's a cost to it. In this case, we're starting to realize these seem like more like steps in the same process instead of separate processes that need to be loosely coupled. So maybe tighter coupling was okay here. Third question we asked, isn't this the same bounding context? Is this the same domain? Definitively, yes, this is. This is the order processing domain for delivery, and we weren't really reaching out or requiring any services at this point. So we were definitely in the same bounding context. Once we answered those questions, we realized maybe a orchestration approach could be a better design. Well, we can't take credit for all those insightful questions. Jan Sui wrote an article called Choreography versus Orchestration in the Land of Serverless. I highly recommend that anyone interested in building a serverless event-driven system read this article. We read that and we were able to ask ourselves those questions and realize that orchestration would be a better approach for us. With that new level of insight, we went back to the whiteboard and redesigned it to use the orchestration approach. So here the customer still places the order through their mobile phone or web app. The order will get sent again to our API gateway. We will still use EventBridge because we wanted that flexibility of still being able to handle events and maybe eventually sending it to another service. But now, instead of EventBridge choreographing all the steps in the workflow, we created an explicit workflow here with step functions. A standard workflow will then be executed to process the order. Notice that we have a nested express workflow. We're going to talk about that more a little later. And we have a callback here. We're going to dive into that a bit later. Key things here is that it immediately became a lot clearer of what's happening. Taking a look into design, if you're going to do an orchestration approach in AWS, step functions is the tool of choice. We still use EventBridge. We didn't kick out EventBridge from our design. It's still used to orchestrate the inbound third-party events, and it still gives you that flexibility if you need to send the other services. Retries, this was very easy to adapt from the previous design. We wrote our Lambda functions to be very lean and single purpose to begin with, so it was actually only a day or so to convert it from the choreographed design to the orchestration design. We use a nested sub-workflow or nested workflow in there. We're going to talk a little bit more about why we did that in cost optimizations, but it's a cool feature if you didn't know. A standard workflow can call a nested express workflow. Retries and things like timeouts are very easily handled in step functions. You just simply declare them in your state machine definition. We really enjoyed that part of step functions, and it's one of the best parts of the service. Finally, it just became very easy to understand and troubleshoot. As you see on the right-hand side, it's clear that these steps are executing in this order. They're in production, you can see if they're green that it succeeded, if it's red it failed, and it allows production services to dig in that way. We can kind of export the diagram and show it to other teams like our product owner and quality engineer, and they just understood it better. So we definitely decided to go down the orchestration approach. I wanted to touch on another cool pattern that we used inside the workflow. We used a callback task token pattern. If you notice, the workflow paused, and what we're doing in the workflow is actually waiting for the delivery to happen. So we can place the order, and maybe up to a few hours later, the delivery will happen, and the workflow will just sit there and wait. The delivery partner will release an event when the driver is actually close to the restaurant. It could be maybe a few minutes from the restaurant, it's configurable. Once that release event is sent back through our API gateway to our EventBridge, we invoke a callback handler. That handler will look up the order ID in the DynamoDB table and send that order task token to the standard workflow and step functions to resume. It was a really cool pattern to handle orders that may be coming in early and the delivery might not happen for a few hours later. Once we decided to design it with the orchestration approach in mind, everything started to fall in place. Let's go through the dev process and CI/CD. We used the serverless framework to deploy and build the application. We've used it for a few years, so we were comfortable with it. There's a couple plugins that I recommend that you check out. One was the serverless IAM roles per function plugin. This ensures that you have best practice of least privilege permissions on each of your Lambda functions. If you don't use this role, it may create a monolithic role that has too permissive permissions for your Lambda functions. We also used the serverless step function plugin. This was another cool thing that we learned. If you want to put your step function definition right into your source control with your Lambda functions, it allows you to put it right into the serverless YAML file. We also made a decision to combine the Lambda and step function workflows in the same project. It was the same developers working on it, so it just made sense for us to keep them together. We haven't had a reason to separate them since. We use the mini middleware for Node.js. So I've said middleware many times, so I don't want to confuse you here. Middleware is referring to a simple wrapper around your Lambda function that could run before or after it runs. In this case, it's great for cross-cutting concerns, such as pulling parameters from parameter store. So we used the SSM plugin to pull in secrets and API keys, which allowed us to connect and communicate with our third-party vendors. We also use GitLab CI/CD for our source control and CI/CD. A cool feature we use is every time a feature branch is created by a developer and checked in and committed, our CI/CD will kick off and create a brand new CloudFormation stack with all the resources required to run the order middleware. This reduces collisions with other developers in the main branches. It allows them to test and break and do whatever they need in these separate stacks. Because it's serverless, it's pay as you go, so you don't have to worry about the cost here except for when you execute it. If you contrast that to EC2 or RDS, would definitely be pricey if you had those resources provisioned. Just remember to clean up your resources after a while because a lot of these stacks can be created. Let's touch on testing next. So we were definitely not experts on serverless testing. We had to do a lot of research to figure out the best way to do this. We quickly realized that unit testing is not as important in serverless apps. A lot of the functions are going to be pretty simple, putting something to a Lambda or a Dynamo table, or maybe putting something into an event bridge event bus. But if you have critical business logic, such as our adapter logic, which converted orders to our canonical format, or validations, that's a good place to put unit tests. So we would use the Jest framework for that. Integration testing is actually a lot more important in serverless. As you saw in the diagrams, there's a lot of services, events going around, and things that are pretty hard to understand and test. So what we would do is we would spin up the live resources, and we would put them in a lower environment, and our integration test would run against them. We chose not to run against mocked AWS services. We did, however, mock out the external APIs in our diagram. This was to facilitate load testing and end-to-end happy path testing of our step function workflows. Let's take a look at that mocked API. As you can see here, it's the same diagram as the orchestration, except we've mocked out the delivery partner on the left-hand side, and we've mocked out the POS API on the right-hand side. We didn't make this too complicated. All we did is we used API Gateway, and we used Lambda functions to mimic the requests and responses. We then used JMeter to replace the customer in this diagram, and we were able to pump in as much load as we wanted to simulate. Basically, when we got to 50% of all orders, what that would look like. Next, let's talk about monitoring and observability for order middleware. We heavily relied on CloudWatch logs and insights. At first, we logged a lot. We logged all the events, all the inputs and outputs, request responses. This is generally a good idea to do at first, and then later you can tune down your logs if you're logging too much, because the cost can add up, especially if your retention policy is not set. We also use CloudWatch Insights a lot to query logs against multiple log groups and look at things like an order ID that's correlated across them. This was a great feature. We also use CloudWatch alarms to let us know when something went wrong or something's about to go wrong. At first, we had failure alarms on both our Lambda functions and step functions. When we first went to production and we went through some scale, we were starting to get a lot of alarms on our Lambda functions. It almost was alarming that it seemed like it wasn't working very well. But when we look a little deeper, 99% or 100% of the step function workflows were succeeding. What was happening is the retries would end up smoothing it out, and they would almost always succeed after an initial failure. So we eventually tuned down and turned off some of those alarms on the Lambda function failures, and it reduced the alarm fatigue. Let's touch on cost optimization next. Cost optimization was something we took very seriously from the start because we knew the scale of what this system would be eventually. Serverless is great for this. It's pay as you go, so when we started out small, it was very inexpensive to run. But we had the ability to calculate how much this would cost at scale by just simply counting the cost, state machine transitions, the Lambda functions, the events. So accurately, we were able to know that this would not be cost prohibitive to us a few years down the line. We also did some tricks like using the nested workflow, the nested express workflow. We did this to save money and also to keep our principles of lean and single-purpose Lambda functions. One alternative is that we could have written more monolithic Lambda functions that did more of the steps in one single Lambda function, and that would have saved money. But we felt like that went against our principles that we had already set to keep them lean. So express workflows allowed us to have the best of both worlds there. We also removed unnecessary step function state transitions in the workflow. In the beginning, it's easy to use basically step functions to do everything, but remember there's a cost for each transition. So some of them we maybe removed or moved to the Lambda function to do. And finally, we tuned the Lambda memory configuration. The Lumigo CLI is a great tool for this. It makes it very easy to pass in different workloads, and it will tell you the recommended size. If you over-provision your Lambdas, you're paying extra for stuff that you don't need. And if you're under-provisioned, it might be running slower or failing more often than it needs to. It's an easy step to do and something I recommend. So let's go through the results of the order middleware. We had a fully functional POC working end-to-end within 2 weeks, and that includes changing from a choreography approach to the orchestration approach. Our estimates were that it would take 2 months, so 2 weeks even shocked ourselves. We were actually in production within 2 months. This included the load testing, going up to scale, ironing everything out with the delivery partner and the POS. So we were so thrilled to get it out that fast to relieve our team members in the restaurants from some of those tablets. We proved that can scale to millions of orders per hour in load testing. So we already reached the 50% in a simulated environment, and it gave us a lot of confidence that this was the right system and the right design. And finally, we were able to add 4 more integrations within 6 months. So the flexible adaptive system we wanted, this definitely was. It was a great success. I'd like to touch on why we think that we were so successful in building the order middleware in such a short amount of time. Well, we have a strong serverless community at Taco Bell. We have a bi-weekly community practice meeting where we come together and discuss architectures and new happenings in the serverless space. We also have a Slack channel where it's with constant chatter of all the new things coming out and comparing and contrasting different designs and services we should do. We've also created starter repos and documentation. It's really easy to get excited about serverless, but we don't want people to lose their momentum because it is a paradigm shift. So having a starter repo has been great for people who want to learn and want to just try it out. We also find that serverless is great to fight imposter syndrome. We're really passionate about fighting that. It's such an ubiquitous thing that many of us software developers have gone through in our careers. What's amazing about serverless is you can kind of do the impossible. Things that seemed impossible before are now possible. And you're deploying early and often to a cloud environment that's very similar to production. You're very superpowered. So we find that that's improved the confidence of our developers a lot. And finally, we feel that serverless democratizes. An entry-level developer was the lead developer on the order middleware. And finally, we want to bring everyone along for the ride. We feel like we're not gatekeeping here with serverless. Serverless is amazing. It allows us to do the impossible. So we want more teams and different departments to work on their own serverless projects. So what's next for Taco Bell? Well, we definitely want to modernize more with serverless. We feel there's more monolithic apps and aging applications that we can modernize. We're going to continue to work closer with the business. The order middleware was a great example of this. Our developers worked right with the product owners, the business sponsors, and the delivery partners to build this so quickly and get it out for real business value. We feel that's the future of how we're going to build applications. We're going to continue to train and upskill the team. They're hungry to learn more about serverless. The results are there. We're just going to continue to make sure we're always learning and supporting them as they go through their serverless journeys. And finally, we want to continue to grow the team. We're always looking for serverless developers. So if you're interested, please check out our website for job opportunities. If you'd like to learn more about serverless, please check out serverlessland.com. Thank you so much for attending our session.